Yeah, welcome everybody to our today's talk within the Design++ speaker series provided to you by the Design++ initiative of ETH Zürich. My name is Michael Kraus and I'm happy to be your host today. And it's my special pleasure to also welcome our guest and lecturer of today, Mr. Timothy Sandy. Before I introduce you to our speaker and his talk, let me shortly provide some background information on our new YouTube channel, which you will find under this link here. The Design++ speaker series is a recurring event where we will provide information about upcoming events in due time via our mailing list, our homepage, and even our YouTube channel. In addition to that, as I said last time, we are happy to share the launch of our new homepage, which you can find here. You can also find updates there on our speaker series, the speakers list, as you can see here, and further activities we are into. And you can also subscribe to our newly designed calendar if you want to. So let me give some short background on the Design++ initiative. At the moment, there is a number of professors in architecture, civil engineering, and computer science from ETH Zürich involved in this Design++ initiative. For the running business, there is this 3 leading postdocs, which you see here. And yeah, meanwhile, we have associated a larger number of scientists to our group. You can find more details on our homepage. And in case you're interested in how AI, machine learning, and XR are connecting to the AEC industry, just reach out to us. We are happy to discuss further project ideas or research proposals with you. Having said that about the background of this Design++ initiative and the speaker series, now let me introduce to you the speaker of today, Mr. Timothy Sandy, which is with ETH Zürich at the moment, and also with incon.ai. Tim received his PhD from ETH in robotic systems in control in 2018. His work focused on robotic sensing and control systems for high accuracy on-site robotic building construction, including the development of the in situ Fabricator mobile construction robot. At the moment, he is also spinning out a company called incon.ai, which aims to use computer vision, digital fabrication, and augmented reality to extend human building capabilities. I gave also the link to his homepage here. Please check out also his papers. And as I said before, all this kind of information will be provided on our YouTube homepage together with the video of this session. Yeah, thanks so far for your attention. This is all from my side, and I will now hand over to Tim.
All right. Yeah, thanks for the introduction, and thanks for inviting me, Danielle and Michael for Michael for organizing. I'm excited to talk to you now about what we're working now, trying to spin out a company called incon.ai, developing digital sensing solutions for the building construction industry. Also motivating kind of how I ended up there, starting from robotics and slowly shifting over to digital guidance systems. So I assume that everybody in the call is either interested in or involved in digitalization in building construction in some way. And the good news is we're really getting somewhere. So now most complex projects are now designed, modeled, planned in sophisticated 3D software. I think this is a significant first step in digitalization in construction. But now what we need is the next step. So the current state of construction projects today is that there's still difficulty getting these 3D models onto the construction site. And therefore, construction companies still need to typically translate these 3D models into some kind of 2D drawing, be it paper plans or maybe digitized plans on a tablet. And then these plans are the main form of communication on the construction site between the building teams. there are obviously some problems with this, and that's first that it takes significant time and effort to generate these 2D plans and make sure that they have all the information that the builders need. Second, as anybody who has assembled IKEA furniture knows, it's difficult to create things in 3D from 2D instructions. And then finally, this analog 2D step breaks the flow of digital information among the members of the construction team, and also makes it very difficult to update the status of your sophisticated 3D models as the buildings are built up over time. So with digitalization, obviously, what we want to do is, in the first step, is remove this analog thing between the digital model and the builders. So remove the 2D step even better altogether and keep everything in 3D, and link the builders directly with the models which contain all the information for the building project. And here we already see a lot of activity. We have like the startup that we're trying to get going here, Incon. We have AR headsets. We have very impressive laser scanners coming out of companies like Leica and other startups that are trying to make productivity apps to help construction projects be better managed. So that's the first step, and then obviously the second step was also a lot of activity, especially ETH, in then now bringing more advanced machinery to the construction site to help the human builders to take on the dangerous, difficult tasks from builders, and hopefully even enable new building processes that we couldn't do using traditional methods. So I think this is the overall vision of digitalization. We're going to zoom in this talk on one specific aspect of that, and that is augmented reality. So I'm sure many of you are also familiar with augmented reality. Maybe you've used some app like this here, Pokemon Go, probably the most prominent example of augmented reality in our everyday life. The general idea of augmented reality is that you want to take virtual information and overlay it on the user's physical surroundings. So in this example, this means that you have the Pokemon, and the woman can view and interact with the Pokemon by looking through her cell phone, viewing the virtual information overlaid on the images of the camera feed. So this has been around for a while. We all have it in our pocket every day. Where I think things start to get really interesting is with apps like this on the right now, which you might have used as well. Both Google and Apple have these measure apps where you can now use the sensors in your cell phone and the algorithms internal to these AR toolkits to actually measure things in your environment, and to really do more interactive work with this AR. And this is really nice, right? It means we add a completely new functionality to our pocket computers, which are already quite capable. Now, in building construction, I think the use of augmented reality is kind of a no-brainer, right? We build 3D models of the things that we want to build. So then the thing that we want to build starts virtual, and we slowly piece together all the pieces to turn it into reality. So it completely makes sense. This is the perfect thing where we would want to be overlaying this virtual information on the builder's environment, giving them exactly all the information they need, exactly where they need it, such that you can build the right way the first time and build efficiently. And we already see a lot of activity here as well. So we have startups like Follogram and Virtual Live developing software to use commercially available AR devices for building construction. We have large construction companies deploying AR systems on construction sites as tests. And I think there's a lot of activity here. But when you dig a little deeper, when you talk to these construction companies about AR, I think the technology is a bit at the state of doing a nice demo, making the cool picture and video, but then putting it aside and waiting for the next developments to come. So I haven't yet come across a construction company that's using AR in their daily workflows. And if you have any pointers, I would be happy to hear about them and hopefully interact with them. So there's still a gap, I think, in this technology that we need to fill to really unlock the full potential. So that brings me to the topic of the talk. So the big question here is, how can we unlock this revolutionary potential of AR in construction? Unfortunately, I don't know the answer, and I wouldn't claim to be offering solutions to such a huge question. But I would like to go through kind of my experiences in research and developing sensing systems for construction, and maybe that can motivate new ways to think about AR systems, and also introduce what we want to do at Incon now, spinning out some of the research into a new company to try to help people build stuff. So with that, I will dig in here. So as Michael introduced, I did my PhD at ETH with the Agile and Dexterous Robotics Lab with Jonas Buchli. This is back from 2015, 2016, the first real experiments we did during my PhD on robotic building construction. So this was together with Katrin Dorfler and Markus Gifthaler, where we wanted to develop mobile robots that could go on the construction site and build impossible structures. And so this was our first attempt at that. We built the in situ fabricator, which is a off-the-shelf ABB arm mounted on a tracked base. And we said, okay, let's try to build a complex brick wall in our lab. And here the real challenge is that as the robot moves around while it's building, it needs to know very precisely where it is relative to this wall that it's building, so that it can lay bricks consistently with the bricks that it laid in the previous building step. And so that's where I dug in first into the sensing system. Okay, how do we localize this robot to build? And here's kind of the simplest thing that I could come up with in order to do that, was that we put a laser scanner on the end effector of the robot. After it moved, it would point its sensor up in the room, take a scan, and then we would then try to fit that scan at the new robot position to a scan we took when we started construction. So that's what these images are here in the middle. You can see the white scan is one we took before the robot started construction. Then after the robot moved, it took this red scan. And then all you need to do is run some optimization problem, which tries to fit these scans together. Excuse me. And from that, you can get the new pose of the robot. And so this works pretty easily. It was more or less off-the-shelf software to do that. And we could get around 1 to 3 centimeters localization accuracy, which is enough to build this curvy brick wall. Luckily, the curviness means it's hard to see these mismatches of a couple centimeters. And another downside here is that it took about 30 seconds at least to process these point clouds. So that meant you would move the robot, it would stop, scan, it would process for a while, and then go and build kind of blindly the next chunk of bricks that it had to build. So moving on from there, what I wanted to do was think is, okay, why does the robot need to scan the whole room in order to lay a brick? The only thing you really care about is where are the bricks. So that was the next idea for the research. Is we said, okay, take the same sensors, take the same robot, but now let's just scan the bricks that we're building. Use the geometric knowledge of what we're building, and relate this scan directly to that geometric knowledge. So here we simply fit a model of the brick into the point cloud. And from there you can know, okay, that's where the robot is relative to the brick. That's where I need to place the next brick. So then the command is more, place the brick 3 centimeters above the last brick. It's not place the brick 3.53 meters from the door on the other side of the room. And then here you see, so this is a very academic exercise we did. Okay, let's have the robot drive around in a circle, reposition many times, and just build a vertical stack of bricks to show that we can reliably relocalize and build accurately without some accumulation of drift over many repositioning maneuvers. It's nice that we didn't solve the automation of the power cord on the robot yet. That came at a later date. But here's what we see. So in this case, we now move to sub-centimeter accuracy. We measured about 5 millimeter accuracy, which when you build a vertical stack of bricks is very visible and looks like a lot. But this should be enough to, certainly enough to build geometrically complex brick walls. And now the processing time is down to about 2 seconds per scan. So we see is huge improvements here as we move from this global localization in the whole room to just local registration of the robot's measurements versus the things that you care about in the scene. And I think that's the first important lesson that we take away when we think about making augmented reality systems. But still, there's something not so satisfying here, and that's that the building process is very sequential, right? The robot moves, it scans, it processes, and then it very blindly then places the brick, and then you repeat that sequential process. The next thing that I wanted to do was really make this a more fluid system, building them more the way that people do. In order to do that, the robot needs to have a constant awareness of where it is, of what it's building. And therefore I switched to camera-based sensing and came up with this system that you see here. So now what I have is a camera and an inertial measurement unit, so accelerometers and gyroscopes. And with these sensors, what we're doing now is locating objects of known geometry. So very similar to the last project where you locate the brick. Here it's locating the bricks and the coffee mugs and tracking where the sensors are relative to those objects really in real time. So that means now on the robot, it's always aware of where it is. It's always aware of what objects around it, and it can always measure how accurately these objects have been placed. And I mean, the system uses extremely basic computer vision with more advanced sensor fusion, and we already see that we can get some pretty nice behavior, pretty nice results here from this system. Now, I think we can dive in a little deeper here to think about how the system works first, since this is kind of the foundation for the first AR system we built. So I'll discuss that in a little bit more detail. Yeah. So the way the system works is you have, so here's a snapshot of me operating the system. You have the camera and the IMU here just off the frame, and you're tracking the sensors relative to these bricks. What the system has, or how it represents the world internally, is there's a set of object meshes. So for every object, it knows the geometry of them, and it knows the relative pose between, in this case, between the bricks. And then it also has some estimate of where the camera is. So this could be some, the camera pose from the last time step, also using the accelerometer measurements to anticipate the sensor motion. So if you know this geometry of the things you're looking at, and you know where the camera is, it means that you can create a synthetic image of what you expect to see. So that means simply taking your meshes of the objects, projecting them into the image plane to build a synthetic image. And that synthetic image is here shown by the white wireframe. So this is kind of where the system expects edges to be in the image, given the objects that it thinks it's seen. So from there, what you can do is you take your expected edges and match them to edges detected in the image. So here, I'm not sure if you can see it in the stream, but there are little green dots along here. These represent places where the detected edges in the image match where we expect them to be. So that's good. That means that the brick edge is where we expect it. Or here, for example, where my finger is, it's expecting the edges to be the edge of my finger, even though the brick model projection would put it here at the white line. But that's okay. We have hundreds of these edge points detected per image. And so all we do is we build a cost function for each of these points. We don't need to understand exactly what this is. This is just representing this distance, kind of what's shown in the red line here. And then we can optimize this cost function to kind of snap the expected image to the actual image that you receive from the camera. And if we repeat this loop over time, every frame, that means now we can really accurately track the sensor motion relative to these objects. So here with the system, we kind of match more or less the accuracy that we had from the last laser experiment. So we have camera localization accuracy on the order of 4 to 5 millimeters when you have good models of the things you're looking at. And now really this real-time behavior. So the system is always aware of what it's looking at. And so there actually, this kind of ended my journey at robotic bricklaying, and you'll see a second how now the story changes quite quickly into AR guidance, and we see things really start to scale up and go into real building projects at building scale. So while I was working on that object tracking system, and I started integrating into the robot, I realized, hey, look, if you have this system which is tracking the objects and you know where the next object needs to go, we actually have an AR system already. So what I did was just pipe in this some kind of building plan, so notion of, okay, where does the next object need to go? You can then specify that to the builder here. On the right side, you can see with these red wireframes that guides them where to build it. And now with the sensing system, because you're actually identifying where each object has been placed, you can actually compare where the object has been placed to where it's supposed to be. And so now here on the left side with this yellow and these blue arrows, the system can now give the builder feedback of, okay, was that brick placed in the right place? If not, then nudge it a little bit to the left in order to align it with your digital plan. And it's kind of neat. I mean, this really kind of just came for free from the system that I made originally from the robots. And then to actually now integrate it into a building process was significantly easier than trying to get a robot to do bricklaying. So now you can leverage the dexterity, the adaptability of a human builder, while really the technical system really just provides this measurement in 3D space that we really have trouble doing kind of with our traditional methods with the measuring tape or with the chalk line. So I think this is a really nice coupling of how the technology can be used by the builder to enable new kinds of construction. And so this was just one day in the lab doing this thing. First time I tried it, it worked with 100 bricks. Wrote a paper and then went away and went back to the robots for a while. But the system kind of pulled projects into itself. So a couple months later, Professors Gramazio Kohler came to me and said, hey, look, we have this project. We want to build some brick walls in Greece. We don't think it works to use robots. Can we try using the AR system? And then a couple months later, there was another project. Hey, we want to build acoustic walls in Switzerland. Can we use the AR system? And it really went kind of quickly. Obviously, it took a lot of work, especially from the deploying the system, bringing it to a level of robustness where it could be used by builders. But here we have two examples where it was really used to build full-scale projects by real builders in real scenarios in a relatively short amount of time. So on the left, this was a project working with Matthias Helmreich from Gramazio Kohler, along with Erna AG, who actually did the construction to build these acoustic timber interior walls where they use the geometrical precision provided by the system to combine aesthetics and acoustics into one building system. And that was in the Basler and Hoffmann cafeteria here in Esslingen, just about an hour away. And then on the right, we have, we built the facades for a winery in Greece. So really with the huge effort of Fotini, Savridou, and Daniela Mitterberger, also from Grammatical Circle Research, we flew the sensing systems there, took a building team, assembled in Greece, and taught them how to use it, and then they went off and built it. And so here we can actually see a look into that construction project. So this was later in the construction. You see there, these guys are now towards the top of the building and one of these, I don't remember, 5 or 6 meter high facades. And it was really neat to see how the builders kind of incorporated this sensing system into their workflow. So like I said, we brought the sensors, we trained the teams how to use them. And then they just kind of went off and used them all day, every day for about 3 months' time. And here we can see what really comes out. And so the way it works is the guy in the background is operating the sensing system. So he has the sensors here in his hand. He has a computer in his backpack. And they're getting the guidance on this screen, which is moved around as they build so that the builder can always see it. The builder is then doing a lot of the bricklaying work. And after he places the brick, then the guy quickly scans the brick, sees the arrows, and then typically just shuts it off, and then they tap the brick into place, into alignment with where it needs to be. And then they found their own methods in how to increase the reliability of the system to make sure that it works for them. And so they took manual measurements of the things they could measure, so like the mortar height on every brick, and on a few bricks, the distance from the brick to the pillar, to make sure that the system didn't drift away. And in this way, they could really build quite efficiently and quite reliably over a long period of time and build this giant structure. And in the end, I think the results are quite impressive. So we believe now this is the biggest structure built in situ using AR guidance to date. And you can really see, I think the project really nicely shows how adding this digital guidance can enhance the capabilities of normal builders. And what really motivates me about the system is that it shows how you can bring a technology somewhere, use local materials, use local builders to build something that you couldn't build otherwise. And really, it was from this project that kind of motivated me to go full-time into this idea of AR guidance and building what we want to build now, which is a platform for instructive construction. So from those projects, let's zoom out a little bit and now think about, okay, what is this AR system that we kind of stumbled upon, and how is it different to the AR systems that are typically used and the ones that we have in our pockets now and use quite regularly. So if you can break an AR system down kind of at the highest level into 2 components here shown in blue. There's the part which is understanding the environment. So that's the thing that's processing your sensor feeds. It's doing the mapping of the user's environment and locating the phone or the headset in that map. And then there's the part that's displaying the augmented content. Now, in a conventional AR system, your object models, so this would be whatever you want to show to the user, whatever content you're augmenting, is used only in this displaying step. So internally to the algorithms, this is what the world looks like. It's building up a map, abstract map of visual key points, which build up a point cloud, and then the camera is located in that point cloud. And these systems are amazingly robust, and they can work in now almost all environments very reliably without any user training or anything. but they reach a level of centimeter level accuracy at best. And they also, because the maps are some abstract representation of the world for construction, that means you need to do a little bit of extra work in order to try to align that map with actually the structure that you're building. So this is very much like the first bricklaying project we did, where you scan your whole room in order to place a brick on the wall. Alternatively, all that we do is we have these object models, and because we're actually building physical things from this content that augmented content that we want to show to the builder, we can now use these object models in the understanding of the environment. And this is a subtle difference, but I think it's a fundamental one. And for an AR system for construction, I think this is a real game-changing thing, because now we can get down to sub-centimeter accuracy, and your map is now really the stuff that you care about in your environment. So that means we can automatically align the sensor's internal reference system to the thing you're building, meaning that we can get zero drift over days and weeks over the course of construction. Now you can see some of the more recent work. So this is just videos I did yesterday to try to show this point. So here is just in my room here, I have an IKEA table also with a CAD model of it. On the left, I just use AR core. So here I placed some anchors. You can see these little green guys around, and manually align the CAD model to the table. But you see, once you kind of change your viewpoint, there's very clear misalignment between the table and the environment. Even though you can track very reliably, you can imagine that if you want to give a builder instructions about how to build the table, this would be enough misalignment that things could get confusing. But now if we use this object model tracking, what we can see is you see the model kind of zooms in and fits the table. And now you can really see this zero drift as we move around, change the viewpoints considerably. And that means that you get this good alignment. Actually, I saw only when I did this that it seemed like either the CAD model's wrong or the legs of my table are a little bent. I could try to bend them back into place if I wanted. But you can really see now that things really snap. So if you want to give instructions to a builder, now you can really point to which leg of the table he should, whatever, be working on, where to insert the screw into what hole. Oops. And then if you go to the next level, sorry, here we go. And now what that means is, okay, nice, you can align a model with a physical object, but now that means we can now take the bricklaying system that we used in Greece and really use it standalone on a smartphone. So this is back last spring. So in the first quarantine, this is how I spent my time playing with children's blocks. But you can see the same behavior of the system as I showed in the early experiment. So you see the red arrows pop up, showing where the brick needs to be adjusted in order to align it with the digital model. And in this way, we can do the most precise toy construction ever. And I think this is where you kind of start to see, okay, everybody has this thing in their pocket now. Everybody could start to build something that they couldn't build before using this system. So at Incon, what we want to do, so now we haven't yet incorporated company, but we're 3 co-founders, and myself, Fadri Fruder, and Abu Gavel. So we've been working on this project for nearly a year now. What we want to build is, so building up upon this kind of core algorithmic stuff, we want to build a platform to guide construction projects digitally. What that means is we want to first be able to connect teams of builders to a shared digital model. And so that means we need to keep track of a live building plan in the cloud and sync them with a set of digital devices. So we target smartphones, tablets, and also AR headsets like the HoloLens. On those devices, we can then provide next step instructions to builders with more intuitive than printed plans. So really show the builder, okay, install the screw here, put the brick here at this point in space. And then finally, use our algorithms, use AI to validate the built structure, make sure the task is done correctly, so that if the builder makes an error, you can raise it to his attention even before he moves on to the next task. And so with that, I'm going to wrap up. And I'd like to end it with a bit of a call to action. So we're trying to build this thing as a platform that can really be used to help people build things and to enhance the creativity of people using digital technology. And for that, I think we're very open to hear any ideas that you might have about where this technology could be applied, where you could do maybe build new things that people couldn't build before using this tightly coupled sensing and digital feedback for construction, or also places where giving builders more intuitive instructions could help build projects more efficiently. So that, I thank you all for your attention, and I'm happy to take any questions.
Thanks again, Tim, for this nice and interesting presentation and the discussion. We very much appreciate your time and efforts for preparing and delivering the talk. As I said before, thanks. As I said before, we will upload the information for Tim and his talk and his startup together with that video on our YouTube channel. And last thing here is to eventually highlight our next talk, which is already next week. This time Thursday, 4 p.m. It will be delivered by Moritz Becher, which is with Disney Research. Due to confidentiality, we are not allowed to have outside of ETH persons within that talk, and we are not going to record it accordingly. Sad, but we have to stick to that rules. And so thank you for your attention, for visiting us, and stay safe and see you next time.